Hey, before the break, we looked at the next step of Django. Um, I'm going to rewrite that the module 6 instructions either this evening or tomorrow, but basically it'll be to set up an account on the Python anywhere.com site and put something small, probably a template, maybe maybe even the app that you did in the previous one or something that you are maybe one of your Django projects you already have, put it on there. But yeah, basically it's going to be set up the account. So I'm just going to look at the URL, skim through the code, and if the page doesn't crash, that's what the points are going to be for. Just make sure it gets deployed correctly, so that when we get to the final project, you know how to already know that you know how to deploy a site. Next up, we got a couple things to look at. Really quick is multi-threading, parallel processing. Draw a quick picture on the board. So, imagine this is our program. So we have the start, and I'm just going to draw it like this. Whatever happens in that flow chart, and then the end of the program. Kind of just has a starting point, goes through all the steps, and then most of the stuff we've written so far works that way. But depending on the situation, we might be able to break that up differently. We don't always have to flow from beginning to end every single time. Like if whatever code is right around here, depends on the stuff above, obviously it has to come afterwards. But maybe we're just doing 3 different things. It doesn't matter which one gets done first, which one gets done last. It doesn't matter the order we do them in, as long as they are all done by the end. That's the situations where we can split that up into multi-threading. So instead of running straight through it, we get our start, and then at the beginning we just jump over to some small piece of code, like a smaller. Through those pictures, kind of look like a thread, trying to look like a thread. Right, that one comes over to there, and afterwards, there's a section that we break out into its own little thing. So not completely like methods, because just methods, we would still, well, we have to have methods. Methods often depend on order still. We still need to worry about the order that they go in. But we would write a method and then be like, okay, we don't care what order these methods run in as long as they all get done by the end. Maybe one more, put it here to kind of match that picture. So we split it up into 3 separate threads, which I kind of drew all the same length. Let me make one of them short and one of them really long. So it's not like an even split. It's where our program could be split up on its own. So not every program fits this situation, because if this section depends on this section of code, which depends on this section of code, there's really only one order we can go through that in. And then when we're done, we just bring all these pieces back together and then finish up at the end. It allows us to jump back and forth. So that's multi-threading. And to go along closely with that is most computers have more than one core. I don't think they even make single core CPUs anymore. It's been a long time since I've heard one. And if they do, it's for something like an alarm clock or coffee maker. We sometimes have a lot of cores to work with. So if we're able to split it up into multiple threads, we can send each of those threads to different cores on that CPU, which really is handled synchronously. Because when we just do multi-threading, we're on the same core, the computer can still only do one thing at a time. So what it would do is it would jump over here and it would do a little bit of this one, then come over here, do some of this one, maybe halfway. Jump back here, do a little bit more of this one. Go over here, do some of that. Finish out the middle one, then head back. And maybe it does a little bit more of this one. Jump over here, finish out this one, then jump over here and finish out this thread. So the computer decides how to jump back and forth between them. So it doesn't just run all the way through this one and then do this one and do this one. So it's jumping back and forth, which still often makes it faster than if it did all the way through the first part, then all the way through the second part, then all the way through the next part. Sort of cleans and some resetting there. So it can be quicker, but with multi-threading, it is still jumping back and forth between the threads. But if we can do this, then we can put each thread on a different core. And then a core is basically an independent CPU. So if we got 4 cores, we could have 4 different threads really running at the same time.
And now they have 2 threads for most of them.
Yeah. 2 threads at any given time. So once we do it, we can do so jumping back and forth, if you do 2 threads per core, there's different numbers depending on the machine. 2 threads per core, we could work through these 2, and then kind of, as it jumps back and forth, it's working on 2 at any given time, or whatever number of cores your particular machine has. So
mostly anything above i5 or Ryzen 5, they have twice the number of threads as they have cores. But i3, those cores do have 4 threads, things like that.
Yes. So when you know which machine you're going to, you can be very detailed. But in general, you can rely on there being multiple cores that can run multiple threads. So we know we'll have it. I'll just create a new file here and go ahead and save it so that I put it in the right spot. And really to get the right spot over in the File Explorer, this is how I do it on Spider usually. I'll go into examples, make a new folder for concurrent. Threads is what we import. I don't want to use that name. Multi. That'll work. I'll just call it multi. That way it's not using any keywords from anywhere. For multi-threading, we will import threading module, which is what I almost called it to begin with. It's like, oh wait, I shouldn't call it that. And we need some sort of function that it can run. Let's define a function. Busy work. And maybe while x is greater than 0, we'll do some stuff and then decrement x so that we eventually do reach 0. I don't know. Well, let's just print for the screen right now. The busy work has been carried out plus x times. So we'll just print that out to the screen so we can see what it's doing. Nothing too fancy in that function, right? Oh, yes. Then we can return at the end, but there's an implied return if we don't return anyway. Okay, don't actually have to do that part. And now that we have that, we can set up our threads. So we have a function. In most situations, we probably want to do this in more than one function, but as always with the class examples, I want to minimize clutter. See the bare minimum part. So we need some names. I'll call it first and assign it threading.thread. So the threading module, we're going to use the thread class. And then there's two things that we need to put in here. First off is the target. And that needs to be what function do we want to run as a callback, because we're not running it yet, obviously. We don't want to run it. We just want to call back to it. So I'll put in busy work, no parentheses. And then we need this args parameter, not the pointer that we usually use for args. Whoever named it actually called it args, which gets confusing because we have that pointer that most people call asterisk args. Whoever wrote this module actually called it args. It's confused me more than once. And then this is a tuple of the parameters to pass into busy work. So maybe like 6. We'll do that 6 times. Then we'll do another one that's about the same. That way we can see threading.thread. Target again equals busy work. Args equals 9 this time. So we'll pass in a different number. Does that make sense? We can split up what this is doing because the second time we do it doesn't depend on the first time we do it.
So first one is going from 1 to 6. The second one is going from 7 to 9. That's what it's doing. Or it's going from 1 to 9.
1 to 9 or 0 to 9. Not the other down. So x is greater than 0, and then we're decrementing. So one goes 6 to 0, and the other one goes 6 to 1, and the other one goes 9 to 1. So yes, but we're going down instead of up. Well, now we just have to start those. So let's start some multi-threading. And then the one at the end can sometimes be optional, sometimes not be optional. It's one I would recommend just go ahead and taking the option anytime. If you have to return stuff afterwards, it's not optional. And if you're not returning things like we're not, it doesn't hurt anything to do this. But it's better, form a good habit to go ahead and do it. We'll say first dot join. So that's this part in the picture where we get back, join our things back together at the end. It's implied with multi-threading. It is not implied when we get to parallel processing in a moment. Second dot join. That'll bring it back together, and then I guess we can print the word finished. Does that make sense? There's not many steps to it. It's all built for us. This is a fairly new addition to Python. We've only had multi-threading for a couple of years. Oh.
These should be capital.
Oh. Put it on predictive text. It probably was on mine. I type threading dot. Oh yeah, I can see it's not showing up. Yeah. Yeah. So sorry, I should probably look at the predictive text occasionally. Oh, why'd that do that? Oh, this is a mistake I've made many, many times. It must be an iterable. So a tuple is an iterable. Sorry, it's not an assignment. It's a parameter. So we need parentheses inside of parentheses. Let me add a space there. A space there so we can see. So the tuple is the parameter we pass into the args method, and then one more parenthesis for calling that. Which normally looks like that when we jam all of them together. But a bunch of parentheses. Square brackets would also work, I suppose. I don't have an error message. Additional argument follows keyword.
It says that.
Oh, Actually, I have to do something different entirely. I'm thinking ahead to the multi-processing. Or sorry, parallel processing, we can do it that way. Args is an assignment. Args equals that, but we need a tuple. All we have is a single value. So put a 6 and leave a comma and then an empty space. I apologize. I'm trying to jump ahead and think I was thinking of the other one for a moment. That empty space after the comma matters. So a number, comma, something in parentheses. It's now obviously a list or a tuple.
That's two values, 6 and none.
Yep. If you didn't hear him from the Zoom call, he said it has two values, 6 and none. Let me clear that from that silly little mistake there. And run that again. There we go. And look at our numbers. Well, it ran all the way through. On something small like this, it's probably going to run all the way through every time. 6, 5, 4, 3, 2, 1. It ran all the way through both times. It didn't really split them up. If we make it bigger, it'll split it through. So 16 and 29. Okay, there we go. It split it up a little. So it did the first one, what, 7 times? Oh, no, it went all the way through, didn't it? No, it went all the way through. It kind of has to be big before the computer's going to split it up. I don't think this computer's going to split up any reasonable examples here. Maybe if we made a different function that did something different. Define tedious, that's in a y, while y, before, for I in range of y, print doing more stuff, plus I. Let's see if this will split up. And then one of these, this one we can change to tedious. I don't think it's actually going to split up there. That's the syntax. I have a feeling it's not going to. No, it did it in order again.
So I put in 20. It did 1004 through 7.
Then it split up.
Yeah, then it did 20. So it went from 1004 to 987, and then it straight up went to 20 in the second thread.
So it jumped to it, but did it finish the other one afterwards?
Yes.
Okay, yeah. So it did jump. So yeah, he went up to the thousands and it worked. So let me try that. 1, 2, 3, 6, and then 29. Nope, mine still went all the way through. Well, I can't scroll up far enough. Yeah, mine didn't change. Mine went straight through. So on something small like this, we can't even. It has to be big before seeing it. Try some different numbers. Danae found it when one of them was up in the thousands. It split up, but maybe if it run 5 or 6 times, it'll just randomly split it up here. Oh, I did once. I saw. There we go. So the busy work 6 times, then it did the doing stuff, and then it split it up. So with small numbers, the computer's not going to decide it's worth it. It needs split up, but you can see it does jump back and forth. But try bigger numbers and run it a few times. You'll see it does different things every time. Fairly straightforward with that. The book covers that as well. So just the assignment there is straight out of the book. Any special notes about parallel processing? Here's multithreading.
Using multi-threading would be efficiency issue, right?
What's that?
Using multi-threading, it would be an efficiency issue.
Yes. It is much more efficient. Well, apparently I lost my notes on parallel processing. Is about the same, a different library. I'm just gonna grab the example from last year, like I did the other day one time, without waiting to 9:30 to do that. That way we can move on to the other thing that I wanted to show, which isn't going to be a finished example. SDEV 220, and then there's last year's. There it is. So this one is very similar. We just have this different library. What we have to do is set up a list to put our things back together in, because they're all going to different cores. So as they get finished, we have to put them somewhere, and then we define a method that we just use. We'll need a method that basically just appends things there. Notice how some useful name, a parameter, and then all it does is append that parameter onto that list that we set up. That's important. Then our busy work, whatever did randomly for busy work last year. So we might need this. This tells us how many cores we have. That's important. So let me create a new file, and I'll start with that. Import multi-processing as MP or something nice and easy to type, because multi-processing seems like the sort of place that's going to have a typo, right? And then that line in the example, mp.pool, mp CPU count. Actually, I'll just count. I'll just copy that. Well, I'll type it. We do need that number. So I'll come down to the main. The first thing we're going to do, see how many cores we got. So the multi-processing module dot pool. What is our pool? And then notice that's not going to be under predicted text. Multiprocessor dot CPU underscore count. Actually, that would be, wouldn't it? Never mind. I was thinking that wasn't going to show up, but CPU count. Choose it from the list to avoid typos, and then we can print that out. I don't think I printed that on this computer, so let's see how many cores the cheapest computer they make at Walmart these days has on it. If there's a single core computer, it'd be this one. I'll give it a useful name real quick. Part. That way we're not using any keywords. Size equal 4. So the cheapest computer off the shelf at Walmart has 4 cores. They do not make single core computers anymore. I haven't seen it in a long time, so this can be a very useful one. Let's just do the same busy work and tedious task. That'll work. So we have those, and then we need up here near the beginning somewhere we need our asynchronous results. That's the biggest thing. Multi-threading is done synchronously, but parallel processing is done asynchronously. So they are completely independent of each other. So the results might come back in a scattered mess, and we don't know what order they're coming back in. So bringing them back together onto the single core that's going to print out the results is the tricky part, or return it to something else. So I'll call it that. Async results is an empty list. And then we'll define a method called collect results. that does take in some sort of parameter. I'll just abbreviate results. And all it does is append it to that list. So a sync results, I can choose it off there, dot append. And whenever we get something back, add it to that list so that we can make sense of it. And then it's fairly similar, right? We got all the information about the cores. Cores.apply. In this case, that's the callback to our function. And then the arguments that we need to pass in. And again, notice that we pass in a list. This time without the extra comma. Args equals just the list or the tuple. We can also do cores.map. And I made two lists last year. If we do apply, it's synchronous. And if we do map, give it a different name. Yeah. So apply it can be done synchronously with apply or map. Notice we only have two parameters. But here we add in that third collect results one to do it asynchronously. So three different ways that we can do it. Asynchronous is probably the preferable one. That way everything's working independently. Synchronous, they still have to stay in contact with each other. But let's do it both ways, kind of like we did here. And you'll notice they should look very, very similar. So once we have our cores, can I copy that? Speed things up here. I can. I'm just going to copy this, kind of speed things up because I wanted to be finished by 8:30. We still got one more thing to look at. Only this time we have the busy work function and the tedious function. And I don't know, I'll do the same thing. So we'll pass in 6 as a list, and we'll pass in 9 as a list. Two different ways of running that synchronously. Am I getting none? Oh, because we didn't return them. Yeah, sorry, we can't print from two different cores at once. I don't know what I was thinking. Parallel processing does have one more requirement, which will hopefully make sense. We can't have two CPUs accessing the monitor at the same time, right? Two cores will be confusing, so we do have to return something. So I'll just call it result. Starts as an empty string, and then instead of printing that, we'll just add it to that result string every time. Plus equals that. And then throw in a line break at the end. Same thing down here. Results starts as an empty string. Then instead of printing, results concatenates with that string, and then a line break, so we can kind of see what's going on. So we're splitting it up to multiple cores and stuff, and then obviously we need to return that back to whatever. I should be consistent there. Let me take the S out of this results. We need to return that to wherever we're to our main, whatever core the main primary thing is, so that we can see the results. There you go. Something looks a little strange though, right? We didn't get all of it. It's still multi-threaded. So when it did multi-threading, it had to go back in and start over. So you will definitely want to play around with that a little bit and see what changes, what doesn't. Let's look at the asynchronous results real quick. So we set up, this is the one we would do more often. Synchronous stuff gets a little bit funny because we're trying to coordinate things and it's still multi-threaded. So we got some from there and then it went to the other one, and then the other thread seems to have disappeared. I don't know where the rest of those threads went. We only got the 6. Should have been 5 more of them. And here we only got the 0, 1, 2, 8. Oh, it looks like we didn't get all of them this time. But here a bunch of them disappeared. So you'll want to play around with the synchronous stuff. Usually we would want to do asynchronous. That's why I started doing that. I'm just going to skip over this. The last I was in last year's example, which is very similar. I'll call it I'll just call it stuff. I can't think of a name, but what matters is its cores apply async. So they apply asynchronous. And then we can see what's the first thing, the callable. What function do we want to run? So let's run it with the busy work function. Then next up is the args, which takes in some iterable. So args equals some sort of iterable. So let's pass in the number 7 maybe to run that this time. And then it's being done asynchronously, so we need to call this collect results. Something has to come back from this. This has to be a return function. So whatever gets returned from there goes into results. Yeah, I can print stuff. And why doesn't it like that? Oh, so after args is our mapping. So where the mapping is that asynchronous results. Since I typed args equals, I can't put a positional parameter after it. Could have left off the args because it's probably better to have the details in the example, right? Mapping equals.
You said we can still put that asterisk, right?
On this side of the equal sign. So you could say that would be a little bit confusing here. So like args equals asterisk args, the pointer.
You said if we put a positional argument before a keyword argument, we can just put the asterisk way in the beginning, and it would.
Not in this case. So the first one doesn't have a default. The rest of them have defaults we can fall back on. But in this case, since there's a mix of filled in ones and unfilled in ones, that would not work quite the same as it would and when we were doing objects and we had all empty parameters. We didn't have any defaults. So in that case, it was able to figure out which names were missing. But it behaves a little bit different than when we work on it. You could try it and see what results you get, but yeah, it would be somewhat consistent to what you're thinking, but not. What? Oh, is it not the mapping results? Oh, callback. Sorry, we don't want mapping. I just went through the list in order. There we go. And we can't really see a difference because by the time it gets back to us, it's put in the order we asked for it. Or is it? So they call busy work 7 times, which should be this. So it did that. Then look at this. That's the one that was missing. Wait, where did it call that from? This is not calling this function, but we're getting the result of that function right here. So you will want to play around with that with simple examples like this. That's why I'm showing it and kind of see what's doing things. Yeah, mapping.
Range map result, maybe that's where it's getting from.
Let's add some extra. So print line break. Maybe a bunch of asterisks and a line. Ever print this one, print a bunch of asterisks and a line, break. Then we should be able to tell which results are which. Oh, it's down here at the end. So we just have something, so we need this part still. Anything else we want to do, you see I put it in last year's example. All the stuff we want to do while we're waiting for this to run, it's going to run independent of anything else we do. Like we can say, so we set it up, and that one runs on its own. We already got it back and printed it. But, well, like we saw earlier, we have to join it. It's no longer optional if it's asynchronous. We need the computer to figure out how to bring it back together. Then we can do other stuff in between. So like print, doing unrelated things here. And then close all those multiple cores and join things back together. What? It's not stuff, sorry. Close all of our cores, close our connection to all the different cores at once. Cores.close and cores.join. Okay, that was just a silly mistake on my part. There we go. Doing unrelated things and stuff still doesn't quite want to print right, does it? We're not seeing those results. So what do we have in there? Check the predictor text dot get ready successful wait. An underscore value, but it's mangled. I don't see a get. I don't see a getter a get value. Or representation, but that should print. That's apparently what that's giving us. Successful. That's just a message. Ready? Get timeout. We get our like how do we get our results? Which is a trick question. Let's scroll it just a little bit. How do we get our results? Where do we put them? Here, right? We put them here, which just appends them onto this list. So there's our results. I forgot what I called it for a moment. I just looked at it. But we put our results into that list. We only see the last one or the first one. Which one are we seeing? We're only seeing the final result because it put them all together. It kept going through the list, printed all that stuff out, and that other core off to the side, this is what happened up here as well. It doesn't have access to the standard output because the one our main is running on has the standard output, which means it only gets a minimum output, so it kept overwriting the previous output. So we only got that last one. With apply, which is synchronous results, and apply asynchronous. So apply, if we have a bunch of things printed out, we'll only see the last one because it's constantly overwriting. But with mapping, we do see all of them. We're getting different results, and you would definitely want to play around, make small changes on small examples like that, now that we've seen the keywords, and get familiar with that. And that took a lot longer than I was expecting it to. Since the other example is only half an example, or would y'all be okay if we wait until Tuesday to cover that? Or sorry, Monday, on the day we have class. Yeah. And then just kind of look at that real quick, because that's the two things on the homework this week. So the other one was just going to try to an example or half an example to show the usefulness of that stuff we're doing. That be okay with everybody? I see check mark on the Zoom call and nods in the room here. And then we still have what, an hour and a half. You can work on the homework and projects and all that other stuff you have coming up, because we are getting very near the end, aren't we? 2 weeks. I've got head nods in the classroom and a big check mark on the Zoom call. So let's put this stuff on GitHub. I'm gonna go ahead and close it here so I don't accidentally make changes. Something I found can be useful over the years. Go ahead and close out of things so you don't to avoid accidental changes. And then I'll just do it on PowerShell. That's the way I'm used to doing Git stuff. So we saw all this before. Works to just drag it over to the web interface to commit to concurrent. This is a good name for it. Git push order. I gotta stop watching the TV across the room. It's like a second behind the keyboard I'm typing on. Makes it very confusing. Okay, so those examples are on GitHub if you want to refer to them. Does anybody have any questions about those things? Hopefully that Django stuff looked a lot easier than doing it all in the terminal that way. Wait, I assume the silence means no questions. If you have any, let me know. I'm always happy to help. Otherwise, I will see you all on Monday.